All right, Calc BC. Today we are talking about lesson 1.3, more limits. And according to College Board's exam description, course description, this is going to be 1.8, 1.14, and 1.15. That's determining limits using the squeeze theorem, connecting infinite limits and vertical asymptotes, and connecting limits at infinity and horizontal asymptotes. You can see here that there are a lot of lessons that we're skipping. Those are somewhat integrated into what we're already doing. Some of it is kind of already obvious since you've had A, B, and then some of it we'll be coming back to later as we continue to review for the AP test throughout the year. So with that, I'm going to switch over to the notes. All right, so here we are, 1.3, more limits. And this is our last lesson in Unit 1. So after this, we'll have some review and a mini assessment in person in the course. But let's take a look. So we've got the squeeze theorem, which is sometimes also called the sandwich theorem. And it says if h of x is less than or equal to f of x, which is also less than or equal to g of x, for all x in an open interval containing c, except possibly at c itself, and if the limit of h of x is L and the limit of g of x, both as x approaches c, is also L, then the limit for f of x is L. All right, so there's a lot of math language going on in there, but basically what this is saying is if we have two functions, one above and one below, and they have a limit at a certain point, if there's another function between them, it has to have the same limit at that point, at that x value. So we're going to take a look at an example to prove this. So in this first question here, if 2 is less than or equal to f of x, which is less than or equal to x squared plus 2 for all x, find the limit as x approaches 0 of f of x, and sketch a graph to illustrate. All right, so just, well, let's just start by looking at the graph. So I'm going to do a rough sketch here. And I know that the line y equals 2 is just a straight line across at a y value of 2. So that's y equals 2. And then we also have x squared plus 2. That's a quadratic, a simple parabola, and the plus 2 means it's shifted up 2 units, right? So it's going to be up here like this. So that's y equals x squared plus 2. And so that's kind of our bounds, right? We've got the 2 on the one side, the x squared plus 2 on the other side. We don't know what f of x looks like. We just know there's something in the middle here. That's our f of x. Maybe it looks like this. We don't know. But we've got some sort of function. We're going to assume that this f of x is continuous. And we want to know the limit as x approaches 0, right? So we're looking right on this y-axis here when x is 0. Okay, so what we need to do is think about the limit as x approaches 0 of 2 and the limit as x approaches 0 of x squared plus 2. And so for our lower function, the 2, as we approach an x value of 0 from the sides, the y value is pretty clearly going to stay 2. It's always 2. And if we take a look at x squared plus 2, as we approach x of 0 from the sides, the y value is also 2. So this dotted function in the middle, the f of x, is going to have a limit of 2 because it's in between the other two. So as we get closer and closer to an x value of 0, this is getting squeezed closer and closer to 2. It doesn't matter what it is over here. By the time it gets to an x value of 0, it has to be at a y value of 2. There's no other options. And up here it even says, except possibly at c itself. So at the point, remember, a limit doesn't really matter what the value of the function is at that point. As long as from the sides we're approaching 2, which we have to be because there's no other option because we're getting squeezed in there, right? The sandwich part of it would be like the upper and the lower functions are like the crust, and then this is like the filling that's getting squished towards the middle. But we usually call it the squeeze theorem. Okay, so that's how the squeeze theorem works. Let's take a look at another example. Graph the given function of the equations. Y equals absolute value of x and y equals negative absolute value of x in the same viewing window on your calculator. Then use the squeeze theorem. So we're going to graph x times sine of 1 over x, absolute value of x, and negative absolute value of x. Let's try it. So we have x times sine of 1 over x. We have absolute value. Remember, that's math, the num tab, and then number 1. And then we have negative absolute value of x. Okay. And look, I can tell right here we're in degree mode, and I don't want that. So we're going to switch to radian mode and then graph again. Okay, can't really see what's going on, so I'm going to zoom in. All right, so a bunch of weird stuff going on right at the origin. We're going to see if we can force the squeeze theorem to apply here. So first I'm going to do a rough sketch of this. We've got this up here, which is our absolute value of x. And then we've got this down here, which is our absolute value of x with negative in front. And then we have our function. So I'm going to break this down into pieces. So if we start with thinking about just the sine of 1 over x. This is sine of something. And 1 over x, you know, that's a whole function on its own. But when we take the sine of something, the answer has to be bounded between negative 1 and 1, right? Think about a sine curve, right? It just kind of bounces up and down. And the peak, the maximums, have a y value of 1, and the minimum is a y value of negative 1. And it's just kind of stuck in there. And it bounces up and down. And you can, you know, if you transform it, it changes in certain ways. But as long as we have the sine of something, it can't go above 1 or below negative 1. So that's already bounded like that, right? Now think about this question. We're multiplying by x. So if we multiply this middle by x, it's almost like we're multiplying the sides by x as well. Now the only thing is we need to think about what we're doing here, because in some sense this is going to make the answer over here work if we leave this as x and negative x, like that. But over here, it's going to get messed up because now the negative x is actually up here and the x is actually down here. So we actually do need to add in these absolute values to make this inequality true. So just by looking at a sine and then multiplying each side by x, we've created this squeeze theorem type of situation, right? So we now know that whatever our function is, and it doesn't actually look like this, but it doesn't matter what kind of crazy curve it is, right? It doesn't matter because we know it's between negative absolute value of x and absolute value of x. Then we know that the limit is the same as the limit of this and the limit of this. And you can tell as x is approaching 0, the y is also approaching 0. So what we can say here is, and I like to use 3 dots. You might have seen that before. It means therefore. It's common in mathematical writing. So we're going to say therefore, due to squeeze theorem, the limit as x approaches 0 of f of x equals 0. And that's because the limit of negative absolute value of x is 0. The limit of absolute value of x is 0. So the limit of the middle one also has to be 0. All right? So there's your squeeze theorem for you. Let's keep going here. Next example, find the limit, draw a sketch for each problem. So the first three questions here, A, B, and C, all are talking about 1 over x minus 3. If we take a look at that graph, it has a vertical asymptote at x equals 3. And the curve looks like this on this side, and it looks like this on this side. Again, that's a rough sketch, but that's what we're working with here. So let's take a look at what we have. If you forget, this little tiny minus sign here means that we're approaching the limit as x approaches 3 from the left, and the plus means x approaches 3 from the right. So let's first think about those. As we're approaching 3, an x value of 3 from the left, the curve is going to be approaching negative infinity, right? This curve is going down forever. It's not approaching a specific number. As we approach an x value of 3 from the right, this curve is approaching positive infinity. And therefore, as we approach 3, the limit does not exist. And this is all about the definition of a limit, right? The definition of a limit is that the left side limit equals the right side limit equals a number that we can put here. And continuity takes that one step further and says that the left side limit equals the right side limit equals the value of the function. That's how you prove that something's continuous, right? But in this case, we weren't asked that. The overall limit doesn't exist because the left and right side limits are not equal. Okay, letter D, the limit as x approaches 3 of 1 over x minus 3 quantity squared. So if we take a look at this graph, we're still dealing with a vertical asymptote at 3. And this time, our curves are both above the x-axis like this. All right. And now we think as x is approaching 3. Well, if we think from the left, it's approaching positive infinity. If we think from the right, it's approaching positive infinity. So overall, we're approaching positive infinity. There you go. Okay. We got a couple more questions, so I'm going to flip the page over here. All right. In pre-calculus, you learned that y equals this double bracket of x is called a step function or the greatest integer function. It means that y is the greatest integer that is less than or equal to whatever x you're plugging in. So let's take a look at this. So I'm going to do, again, a rough sketch here. I'd like you to do the same. So let's take a look at the limit, and we're going to sketch the function double bracket or greatest integer function of x minus 2. So if I plug in 0, 0 minus 2 is negative 2. And that's going to be true all the way until we get to an x value of 1, where we're going to bump up to the next integer. So this is what the greatest integer function looks like. And you can see why it's sometimes called the step function, because it looks like steps, right? So let's take a look. The limit as x approaches 1 from the left. So as we approach an x value of 1 from the left, our y value is approaching negative 2. As we approach 1 from the right, our y value is approaching negative 1. So because our left and our right side limits don't agree, they're not the same, the overall limit does not exist. Sometimes you need to use the properties of limits to make the problem easier. Let's try this example. Find the limit, draw a sketch for each problem. Okay. So there's a property of limits that says that if you multiply two equations or two separate limit statements together, it equals the same as the limits combined. So we're actually going to separate this. So here's what I mean. Limit as x approaches 2 from the left. I'm going to split this into x cubed times absolute value of x minus 2 over x minus 2. And now what I can do is change this into limit as x approaches 2 from the left of x cubed times the limit as x approaches 2 from the left of absolute value of x minus 2 over x minus 2. Okay, and the limit as x approaches 2 from the left of x cubed. Well, x cubed is a continuous function. We don't really have to worry about coming from the left or coming from the right. We can just plug in 2. Direct substitution, right? So 2 cubed is 8. And then what do we do with this one? So approaching 2 from the left of absolute value of x minus 2 over x minus 2. If you're not sure, let's take a look at the graph. I'm going to plug that in really quick here. And so it's really like dividing something by itself. So it's always either going to be +1 or -1 because of the absolute value. And at x equals 2 is where it switches. So we're approaching from the left. So it's going to equal -1. And if we wanted to do a rough sketch of that, we could. I'm not going to actually force us to draw a sketch here. I think this is fine. So we have 8 times -1, so we get -8. So sometimes we can split up limits like this to help simplify the process, because that was a lot easier than trying to figure this out in the original problem. Last thing here, 3 more examples. Note, be careful when applying the properties of limits. If this approach leads to a result of 0 times infinity, the limit properties do not help you determine the answer. 0 times infinity is an indeterminate form. We will study limits of indeterminate forms later in the year. Maybe the bell might be ringing in your head to remind you that this has to do with L'Hopital's rule. We'll be talking about that later. On the next example, if you try to use the limit properties, you will get the wrong wrong answer rather. So let's try this first question here. So the limit as x approaches 3 from the right of x squared minus x minus 6 over x minus 3. So what is this note talking about? So if we thought about splitting this using properties of limits, just like we split this into 2 multiplication, 2 limits multiplied, we could split this into 2 limits divided. So if we tried, we could have the limit as x approaches 3 from the right of x squared minus x minus 6 over the limit as x approaches 3 from the right of x minus 3. If you try that, you can plug 3 into both. So there's going to be 9 minus 3 minus 6. So you're going to get 0 over 3 minus 3 over 0. So this is indeterminate form. Which is not the answer. So instead, we have to figure out a different way to solve this. And if you remember L'Hopital's rule, you're welcome to use that now. I'm going to actually do it by crossing off factors. So we're going to have the limit as x approaches 3 from the right. X squared minus x minus 6 can factor into x minus 3 times x plus 2. And if we do that, now the x minus 3's can cancel, and we're left with limit as x approaches 3 from the right of x plus 2. Now we can use direct substitution. 3 plus 2 is 5. And the 3 from the right actually didn't end up mattering in this question. Didn't matter that it was from the right. Now remember, this process right here is eliminating the whole. It's eliminating the point discontinuity so that we could use direct substitution. Let's try 2 more examples. So in this next one, for this expression, we're going to split it like we did 2 examples ago. So it's going to be the limit as x approaches 2 from the left of 3x times the limit as x approaches 2 from the left of absolute value of x minus 2 over x minus 2. And then we can plug into, for the first part, we're going to get 3 times 2, which is 6. And for the second part, we can take a look at the graph again if we want. It's actually the same exact limit that we just did up here. And the answer was -1. So it didn't change. It's still the same question. So it's -1. And so we have -6. And the last one, we have a step function. And we're going to do the same thing. So we're going to split it into 2. And for the first part, we have the same exact limit that we just had up here, so it's 6. And for this part, okay, we have a step function, x minus 2 over x minus 2. So if we plug in 2, right now we get 0 over 0. But what's going on with this step function? I think we might have to graph this. So if you are wondering how to graph a step function, it's in the same known tab where the absolute value is. It's number 5, int. Oh, geez. There we go. Okay. An integer function of x minus 2 over x minus 2. Let's take a look at the graph. Oh my goodness, that is crazier than I was expecting. X approaches 2 from the left. Wow, okay. So according to this, that looks like it is approaching something crazy, like infinity. Does that make sense? Let's think about that. So x approaches 2 from the left. So as x approaches this top part from the left, just x minus 2, it would be -1. And then on the bottom, as we plug in numbers approaching 2. Yeah, okay. Yeah, so we've got something crazy here. So as we approach 2 from the left here, that infinity is going to be stronger than the 6, and we're going to end up with infinity. That's not what I was expecting. I don't have that on my answer key. I think I did this question wrong last time that I did it. If I have a correction later on, I will add it to the notes on Edpuzzle so that you'll see it on the screen. But that's what I got right now. Hopefully that makes sense to you. If you have any questions, let me know. Thank you very much, and that's the end of the notes.